Over the past few years, a number of methods have surged to solve the problem of grasping arbitrary objects in a data-driven manner for single-arm robotic systems. Some typical work, like Dexterity-Aware, can even use two or more heterogeneous ND factors to ambidextrously pick things from the bin. However, most of these works focus on picking tiny things even with dual-arm robot. The key advantage of the dual-arm manipulator system is far from being fully exploited, since arm cooperation is missing. A dual-arm robot can manipulate large and heavy objects like a chair, a lamp, or even a screen by dual-arm cooperation. But how does the robot know where it can grasp? An intuitive idea is to directly use two grasp poses generated by the state-of-the-art approaches and allocate them to the dual-arm manipulators. However, this is infeasible in practice. For example, it is challenging to generate and select more feasible and reasonable grasp pairs for dual-arm manipulation from the astronomical number of pairwise grasp configurations obtained by random combination. To explore this, we propose a dataset and a baseline method with some real robot experiments. This is the first large-scale dual-arm dexterity-aware grasp dataset, which we'll call it DA2. This dataset aims at filling the gap in the research field of vision-guided dual-arm grasping. The dataset contains a total of about 8 million parallel jaw grasp pairs for 7,000 different meshes. The grasp pairs are labeled with various grasp dexterity measures by fully analyzing the grasp matrix. The data sources used in this work are from Shaplet. For each object, a refined block antipodal sampling is used to divide the bounding box of the original object to enable parallel generation of single grasps. Then, a large number of grasp pair candidates can be extracted by random compilation, from which we can select feasible grasp pairs with various dexterity labels to form a balanced dataset. Finally, the grasp pair candidates not fail in force closure inspection are eliminated in the dataset. We additionally propose an evaluation model as a baseline to inference the grasp measures for each grasp pair through point cloud input. With the DA2 dataset, synthetic points are rendered through virtual cameras during the training period. The generated point cloud inside the grippers are then transformed to the object coordinate system to eliminate the ambiguity caused by the different experimental setup. In the experiment, the trained model with GPG algorithm is deployed on the dual-arm kilowatt Gen 3 manipulators with self-designed grippers. The visual sensors used in this experiment are two calibrated K-Lect Azure cameras. Video clips for the successful grasp of the box, the tripod, are presented here. For the yellow stool, low feasible grasp pair can be generated, while for the gray stool, a robust grasp pair and an unstable grasp pair are generated, which respectively result in successful grasp and grasp failure. The average success rate of the dual-arm large object grasping in the experiment is around 66%.